Welcome. In this video, we will explore applications of differentiation, a core topic in IB mathematics analysis and approaches higher level. Specifically, we will focus on two key areas: modeling with differential equations and optimization. By the end of this session, you will be able to solve problems involving rates of change and find maximum or minimum values of functions, which are essential skills for the HL curriculum. Let's begin with a modeling problem. We'll analyze the growth of a bee population using a logistic model. The number of bees in a hive after 2 months is modeled by the function b of t equals 3,000 divided by the quantity 1 plus 0.5 times e to the power of negative 1.73 t. Our first task is to find the initial bee population. This means we need to find the value of b when t, the time in months, is 0. So we substitute t equals 0 into our function. This gives us b of 0 equals 3,000 divided by 1 plus 0.5 times e to the power of 0. Remember that any non-zero number raised to the power of 0 is 1. So e to the power of 0 is 1. Our expression simplifies to 3,000 divided by 1 plus 0.5 times 1. This is 3,000 divided by 1.5, which equals 2,000. Therefore, the initial bee population is 2,000. Next, we need to find the percentage increase in the population after 1 month. To do this, we'll first calculate the population after 1 month, b of 1, and then use the percentage change formula. Substituting t equals 1 into our function, we get b of 1 equals 3,000 divided by 1 plus 0.5 times e to the power of negative 173. Using a calculator, e to the power of negative 1.73 is approximately 0.177. So, b of 1 is about 3,000 divided by 1.0885, which is approximately 2756 bees. Now we calculate the percentage increase. The formula is the change in population divided by the initial population, all multiplied by 100. The percentage increase is b of 1 minus b of 0 divided by b of 0 times 100. Plugging in our values, we get 2756 minus 2,000 divided by 2,000 times 100. This gives us 756 divided by 2,000, which is 0.378. Multiplying by 100, we find a percentage increase of 37.8%. Part C asks if there is a limit to the population size, and if so, what it is. This is a question about the long-term behavior of the function, which we can find by taking the limit as t approaches infinity. We need to evaluate the limit of b of t as t goes to infinity. Let's consider the exponential term, e to the power of negative 1.73t. As t becomes very large, the exponent negative 173 becomes a very large negative number. So, the value of e raised to a very large negative power approaches 0. Therefore, the limit of our function becomes 3,000 divided by 1 plus 0.5 times 0, which is simply 3,000. This means there is a limit to the population size, and it is 3,000 bees. This is known as the carrying capacity of the environment. Now for part D, we need to find the derivative of b of t, b prime of t, and use it to explain why the population is always increasing. Finding the derivative will tell us the rate of change of the population. We can rewrite b of t to make differentiation easier. b of t equals 3,000 times the quantity 1 plus 0.5 e to the negative 1.73 t, all raised to the power of negative 1. We will use the chain rule to differentiate this expression. The derivative, b prime of t, is 3,000 times negative 1, times the inner function to the power of negative 2, times the derivative of the inner function. The derivative of the inner function is 0.5 times e to the negative 1.73 t, times the derivative of the exponent, which is negative 1.73. Multiplying everything together, we get b prime of t equals 2595 times e to the negative 1.73 t, divided by the square of 1 plus 0.5 e to the negative 1.73 t. Now let's analyze this derivative. For any real value of t, the exponential term e to the negative 1.73 t is always positive. The denominator is a square, so it is also always positive. A positive number divided by a positive number is always positive. Since b prime of t is always greater than 0, the rate of change of the population is always positive. This means the bee population is continuously increasing over time. For part E, we need to find the rate at which the population is increasing after 6 months. This is a direct application of our derivative. We need to evaluate b prime of t at t equals 6. Substituting t equals 6 into our derivative formula, we get b prime of 6 equals 22595 times e to the power of negative 10.38, divided by the square of 1 plus 0.5 e to the power of negative 10.38. The term e to the power of negative 10.38 is a very small number, approximately 0.031. Plugging this into our expression, we get approximately 0.0804 divided by 1.00031 squared, which is approximately 0.00804. So, after 6 months, the population is increasing at a rate of about 0.08 bees per month. Notice how this rate is much smaller than the initial rate of increase. This is characteristic of logistic growth, where the growth rate slows down as the population approaches its carrying capacity. Finally, for part F, we need to sketch the graph of b of t. We can use the information we've gathered to create an accurate sketch. First, let's plot the key features. We know the initial population is 2,000, so the graph starts at the point 0, 2,000. We also know the population approaches a limit of 3,000. This means there is a horizontal asymptote at y equals 3,000. We determine that the population is always increasing, so the curve must always be rising. We also know the rate of increase is highest at the beginning and slows down as it approaches the asymptote. Putting this together, the graph starts at 2,000, rises steeply at first, and then curves to approach the asymptote at 3,000, never quite reaching it. This S-shaped curve is the classic shape of a logistic growth model. Now, let's shift our focus to the second major application of differentiation: optimization. Optimization is the process of finding the maximum or minimum value of a function. This is often called finding the optimal solution. In IB mathematics, we primarily use differential calculus to solve optimization problems. The key idea is to find the turning points of a function. A turning point, or stationary point, occurs where the gradient of the tangent to the curve is 0. Mathematically, this is where the first derivative, f prime of x, equals 0. However, it's crucial to understand that a turning point is not always the maximum or minimum value of the function over a given interval. Consider this graph. It has a local maximum and a local minimum where the derivative is 0. But the overall or global maximum value occurs at the endpoint x equals b. The global minimum occurs at the local minimum x equals p. This highlights the importance of checking endpoints. Once we find a stationary point where f prime of x equals 0, we need to determine if it's a local maximum or a local minimum. We have two primary tests for this. The first is the sign diagram test, also known as the first derivative test. This test involves examining the sign of the first derivative on either side of the stationary point. If the derivative changes from positive to negative as we pass through the point, the function is increasing and then decreasing, indicating a local maximum. Conversely, if the derivative changes from negative to positive, the function is decreasing and then increasing, indicating a local minimum. The second method is the second derivative test. This test uses the concavity of the function at the stationary point. If the second derivative, f double prime of a, is negative, the curve is concave down, which means we have a local maximum. If the second derivative is positive, the curve is concave up, indicating a local minimum. If the second derivative is 0, the test is inconclusive, and you must use the sign diagram test instead. Let's walk through a standard problem-solving method for optimization. This 6-step process will help you tackle any optimization problem systematically. Step 1. Draw a large, clear diagram of the situation. This helps you visualize the problem and label variables. Step 2. Construct a formula for the quantity you want to optimize. This formula should be in terms of a single variable. Also, determine the domain restrictions for that variable. Step 3. Find the first derivative of your formula and set it to 0 to find the stationary points. Step 4. Use either the sign diagram test or the second derivative test to classify each stationary point as a local maximum or minimum. Step 5. Identify the optimal solution. Remember to also check the values of the function at the endpoints of your domain, as the global maximum or minimum can occur there. Step 6. Write your answer in a clear sentence, making sure you've answered the original question. Let's apply this method to a classic problem, the cake dish. A rectangular cake dish is made by cutting out squares from the corners of a 25 cm by 40 cm sheet of tin plate and folding up the sides. We want to find the size of the squares that will produce a dish with the maximum possible volume. Step 1. Draw a diagram. We have a rectangular sheet. We'll cut out squares of side length x from each corner. When we fold up the sides, x will become the height of the dish. Step 2. Construct the volume formula. The original length is 40 centimeters. After cutting out 2 squares of side x, the new length of the base will be 40 minus 2x. Similarly, the width will be 25 minus 2x. The height is x. So, the volume 5 is length times width times height, which is 40 minus 2x times 25 minus 2x times x. Expanding this, we get v of x equals 4x cubed minus 130x squared plus 1000. Now for the domain. The side length x must be positive. Also, the width of the base, 25 minus 2x, must be positive. This means 2x must be less than 25, so x must be less than 12.5. Our domain is 0 is less than x is less than 12.5. This domain is crucial for our final answer. Let's continue with the cake dish problem. We have our volume function v of x equals 4x cubed minus 130x squared plus 1000x. Step 3. Find the first derivative. V prime of x is 12x squared minus 260x plus 1000. To find the stationary points, we set the derivative to 0. We can factor out a 4. This gives us 4 times the quantity 3x squared minus 65x plus 250 equals 0. We can solve this quadratic equation using the quadratic formula or by factoring. Factoring gives us 4 times 3x minus 50 times x minus 5 equals 0. This gives us 2 possible solutions. X equals 50 over 3 or x equals 5. Now we must check these against our domain, which was 0 is less than x is less than 12.5. The value 50 over 3 is approximately 16.7, which is outside our domain. So we discard it. The only valid stationary point is x equals 5. Step 4. Classify the stationary point. Let's use a sign diagram for v prime of x. We test a value to the left of 5, say x equals 1. V prime of 1 is positive. We test a value to the right of 5, say x equals 6. V prime of 6 is negative. Since the derivative changes from positive to negative, we have a local maximum at x equals 5. Step 5. Identify the optimal solution. Since we have a single local maximum within our domain and the function is continuous, this local maximum is also the global maximum. The maximum volume occurs when x equals 5. Step 6. Write the answer. The maximum volume is obtained when 5 centimeters squares are cut from the corners. Let's look at another example, this time involving surface area. A 4-liter container must have a square base, vertical sides, and an open top. We need to find the most economical shape, which means the one that minimizes the surface area of material needed. Step 1. Diagram. Let the side length of the square base be x and the height be y. Step 2. Construct the formula. We want to minimize the surface area. A. The area consists of the square base and 4 rectangular sides. So A equals x squared plus 4x. This formula has 2 variables, x and y. We need to eliminate 1. We can use the given volume information. 4 liters is 4,000 cubic centimeters. The volume phi is x squared y, so 4,000 equals x squared y. We can solve for y. A y equals 4,000 over x squared. Substituting this into our area formula, we get a of x equals x squared plus 4x times 4,000 over x squared, which simplifies to a of x equals x squared plus 16,000 over x. The domain for x is greater than 0 since it's a length. Let's finish the container problem. We have our area function a of x equals x squared plus 16,000 over x. Step 3. Find the first derivative. A prime of x is 2x minus 16,000 in x to the power of negative 2, or 2x minus 16,000 over x squared. Set the derivative to 0 to find stationary points. 2x minus 16,000 over x squared equals 0. This gives 2x cubed equals 16,000, so x cubed equals 8,000. The only real solution is x equals 20. Step 4. Classify the stationary point. Let's use the second derivative test this time. A double prime of x is 2 plus 32,000x to the power of negative 3. Evaluate a double prime at x equals 20. We get 2 plus 32,000 over 20 cubed, which is 2 plus 4 equals 6. Since a double prime of 20 is positive, we have a local minimum at x equals 20. Step 5. Optimal solution. The minimum surface area occurs when x equals 20. We can find the corresponding height y using our volume equation. Y equals 4,000 over 20 squared, which is 10. Step 6. Answer. The most economical shape has a square base of 20 centimeters by 20 centimeters and a height of 10 centimeters. Let's tackle a more complex problem involving geometry and trigonometry. We have an athletics track with a perimeter of 400 meters. It consists of 2 straight sections of length L and 2 semicircular ends of radius x. We want to find the dimensions that maximize the area of the shaded rectangle inside the track. Step 1. Diagram. The shaded rectangle has length L and width 2x. Step 2. Construct the formula. The area of the rectangle is A equals L times 2x. This has 2 variables. We need a constraint. The perimeter is 400 meters. The perimeter is the sum of the 2 straight sections and the circumference of the 2 semicircles, which form a full circle. So 2L plus 2px equals 400. We can solve for LL equals 200 minus pi x. Substitute this into the area formula. A of x equals 200 minus pi x times 2x, which expands to 400x minus 2 pi x squared. For the domain, x must be positive. Also, the length L must be positive, so 200 minus p x must be greater than 0. This means x must be less than 200 over pi, which is about 63.7, so 0 is less than x is less than 100 over pi. Let's complete the athletics track problem. We have our area function a of x equals 400x minus 2 pi x squared. Step 3. Find the first derivative. A prime of x is 400 minus 4 pi x. Set the derivative to 0. 400 minus 4px equals 0. Solving for x, we get x equals 100 over pi. Step 4. Classify the stationary point. Let's use the second derivative test. A double prime of x is negative 4 pi. Since this is a negative constant, it's negative for all x. Therefore, we have a local maximum at x equals 100 over pi. Step 5. Optimal solution. The maximum area occurs when x equals 100 over pi. We can find the corresponding length L. L equals 200 minus pi times 100 over pi, which is 200 minus 100 equals 100. The maximum area is L times 2x, which is 100 times 200 over pi, or 2,000 over pi square meters. Step 6. Answer. The area of the rectangle is maximized when the radius of the semicircles is 100 over pi meters, and the length of the straight sections is 100 meters. The maximum area is 2,000 over pi square meters. Let's try one more example, this time from the exercise section. A duck farmer wants to build a rectangular enclosure of area 100 square meters. One side of the enclosure is an existing fence, so the farmer only needs to buy wire for the other 3 sides. We want to find the dimensions that minimize the length of wire needed. Step 1. Diagram. Let the sides adjacent to the existing fence be x and the side parallel to the fence be y. Step 2. Construct the formula. We want to minimize the length of wire, L. The wire is used for the 2 sides of length x and 1 side of length y. So L equals 2x plus y. We need to eliminate y. We use the area constraint. The area is 100 square meters. The area is x times y, so xy equals 100. This means y equals 100 over x. Substituting this into our length formula, we get L of x equals 2x plus 100 over x. The domain for x is greater than 0. Let's complete the duck farmer problem. We have our length function L of x equals 2x plus 100 over x. Step 3, find the first derivative. L prime of x is 2 minus 100x to the power of negative 2, or 2 minus 100 over x squared. Set the derivative to 0. 2 minus 100 over x squared equals 0. This gives 2x squared equals 100, so x squared equals 50. The positive solution is x equals the square root of 50, which is 5 times the square root of 2. Step 4. Classify the stationary point. Let's use the second derivative test. L double prime of x is 200x to the power of negative 3, or 200 over x cubed. Since x is a length, it must be positive. Therefore, L double prime of x is always positive. This means we have a local minimum at x equals 5 times the square root of 2. Step 5. Optimal solution. The minimum length of wire occurs when x equals 5 times the square root of 2. The corresponding value for y is 100 divided by 5 times the square root of 2, which simplifies to 10 times the square root of 2. Step 6. Answer. The minimum length of wire is 20 times the square root of 2 meters, which occurs when the sides adjacent to the fence are 5 times the square root of 2 meters long, and the side parallel to the fence is 10 times the square root of 2 meters long. Let's recap what we've covered. We've seen how differentiation is a powerful tool for solving real-world problems. Remember the key steps for optimization. Draw a diagram, create a single variable function, find its derivative, test stationary points, and check endpoints. Mastering this process is essential for success in HL mathematics. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try to solve them on your own before watching the solutions. Question 1. A manufacturer's profit function is P of x equals negative 0.022x squared plus 11x minus 7 or 20. Find the production level x that maximizes profits. Question 2. A 60 cm length of wire is bent into a rectangle with length x and width y. Find the dimensions of the rectangle that maximize its area. Question 3. A circular piece of tin plate with radius 10 cm has 3 segments removed. The remaining area is given by A equals 50 times the quantity theta plus 3 sine theta. Find the angle theta that maximizes the area. Question 4. The population of wasps is modeled by P of t equals 5,000 divided by 1 plus 1,000 d to the negative 0.5 t. Find when the wasp population is growing fastest. Question 5. 2 corridors meet at right angles and are 2 meters and 3 meters wide. A thin metal tube of length L must be kept horizontal as it moves around the corner. Find the minimum possible length of the tube. Let's go through the solutions. First, question 1. We need to maximize the profit function P of x equals negative 0.02x squared plus 11x minus 720. Find the derivative. P prime of x equals negative 0.044x plus 11. Set it to 0. Negative 0.044x plus 11 equals 0. Solving for x, we get x equals 11 divided by 0.044, which is 250. The second derivative is p double prime of x equals negative 0.044. Since this is negative, we have a maximum. So the production level that maximizes profits is 250 items per day. Now for question 2. We have a 60 centimeter wire bent into a rectangle. We want to maximize its area. From the perimeter, we get x plus y equals 30, so y equals 30 minus x. The area function is a of x equals x times 30 minus x, which is 30x minus x squared. The derivative is a prime of x equals 30 minus 2x. Setting it to 0 gives x equals 15. The second derivative is a double prime of x equals negative 2, which is negative, so it's a maximum. When x is 15, y is 30 minus 15, which is also 15. The dimensions that maximize the area are 15 centimeters by 15 centimeters, a square. Let's solve question 3. We need to maximize the area function A equals 50 times the quantity theta plus 3 sine theta. The derivative with respect to theta is a prime of theta equals 50 times 1 plus 3 cosine theta. Set it to 0. 1 plus 3 cosine theta equals 0. This gives cosine theta equals negative 1/3. The second derivative is a double prime of theta equals negative 150 sine theta. For the angle theta where cosine is negative 1/3, sine theta is positive. Therefore, A double prime is negative, indicating a maximum. The angle that maximizes the area is theta equals arcos of negative 1/3. Next, question 4. This is a rate of change problem. We need to find when the population is growing fastest, which means we need to maximize the rate of growth. P prime of t. Solution 4, p per t equal 5,000. 1 plus 1,000, 0.5. First, find p prime of t using the chain rule. This gives p prime of t equals 25 e to the negative 0.5 t, divided by the square of 1 plus 1,000 to the negative 0.5 t. To maximize p prime of t, we need to find its derivative, p double prime of t, and set it to 0. This is a complex calculation, but it's a standard result for logistic functions. The rate of growth of a logistic function is maximized at its point of inflection, which occurs when the population is exactly half of the carrying capacity. The carrying capacity is 50,000, so we set p of t equal to 25,000. 5,000, 1 plus 1,000 t 0.5 equals 25,000 toadas. Solving this equation, we find that e to the negative 0.5 t equals 1 over 1,000. Taking the natural logarithm of both sides, we get negative 0.5 t equals negative ln of 1,000. So t equals 2 times the natural logarithm of 1,000, which is approximately 13.8 weeks. Finally, question 5. We need to find the minimum length of a tube that can be moved around a right-angled corridor corner. Let theta be the angle the tube makes with the 3-meter wall. Using trigonometry, the length L can be expressed as 3 secant theta plus 2 cosecant theta. The derivative is L prime of theta equals 3 secant theta tangent theta minus 2 cosecant theta cotangent theta. Setting this to 0 and simplifying gives tangent cubed theta equals 2 over 3. So, theta equals the arctangent of the cube root of 2 over 3. This is the angle that minimizes the length. Substitute this value of theta back into the length formula. After some algebraic manipulation, the minimum length L is found to be the cube root of 36 plus the cube root of 16, which is approximately 7.02 meters. That concludes our session on applications of differentiation. We've covered modeling with differential equations and the powerful technique of optimization. You are now equipped to find rates of change, identify limits, and solve complex problems by finding maximum and minimum values. Keep practicing these methods, as they are fundamental to higher-level mathematics. Thank you for watching.